So the aim is to be able to store items efficiently. We would like to insert items as fast as possible, and we would like to remove items from the linked list as far as possible. We have been talking about arrays, and we came to the conclusion that arrays are working extremely fine if we know the index of the item we would like to manipulate. But of course, there may be several issues. For example, if we want to insert value 20 in the array data structure with index 1, then what's going to happen? Because there is already a value in the array data structure with index 1, what do we have to do? We have to shift all the items one step downwards in order to be able to insert the value 20. So it has a ortho and linear running time complexity because the items must be shifted, and in worst case scenario we have to shift all the items if we want to insert a new item with index 0. And this is exactly why linked list data structures came to be, because it is extremely efficient to manipulate the first items when using linked list data structures. Okay, so arrays have a huge disadvantage, which means that there may be holes in the data structure and we have to shift several items. And of course, this problem can be eliminated by linked lists, because in the linked list data structure we have independent nodes. These nodes are going to contain the given information, for example, integers, floating point numbers, custom objects, and so on. And what's extremely crucial, that these nodes are connected by references. So as far as linked list data structure is concerned, we have access to the first node of the linked list exclusively. This is called the head node, and other items can be accessed starting with this node. And what's crucial, that the last node of the linked list is pointing to a null. So basically this is how we can traverse a linked list, that we have to start with the head node, okay, and then we have to follow the references until we come to the conclusion that the reference is pointing to a null. This is when we know for certain that it is the last node in the linked list data structure. Okay, so every single node stores a data. It can be an integer, it can be multiple floating point numbers, it can be a Boolean variable, it can be a custom object, and it stores a given reference pointing to another node in the linked list. So every node stores the data itself and the reference to the next node in the linked list data structure, and this is why linked lists need more memory than arrays, because we have to store the pointers pointing to the next node in the data structure. But of course it has a huge advantage, which means that there cannot be holes in the data structure, so there is no need for shifting the items. And this is why ortho and linear running time complexity approaches can be reduced to even ortho 1 constant running time complexity. Okay, so linked list is quite an easy data structure. It is quite easy to understand what's happening under the hood. Basically, we have nodes in a linked list storing the given data, and every single node has a so-called reference that is pointing to a next node in the data structure, and that's all about the theory behind linked list. So it is quite easy to understand and it is quite easy to implement it. What's crucial, that the items are not stored right next to each other in the main memory, so there is no random indexing. So we are not able to access the given items based on given indices in ortho 1 constant running time complexity, and this is one of the main disadvantages of linked lists. So as far as arrays are concerned, we have random indexing, but it is not true for linked lists, because the items are not stored right next to each other in the memory. And we can implement more complex data structures and abstract data types with linked lists, such as stacks and queues. The main problem is that finding an arbitrary item in a linked list still has ortho and linear running time complexity, and this is exactly why we have to talk about more complex data structures such as binary search trees and hash tables or dictionaries in Python. Okay, in the next lecture we are going to talk about the